In this section, we're going to be going over exponential growth and decay. So in nature, a lot of quantities will grow or decay at a rate proportional to their size. So for example, if we have a function f of t, and it represents the number of individuals in a population, or it represents the number of bacteria at time t, then it seems reasonable to expect that the rate of growth, which is f prime of t, is proportional to the population f of t. So what proportional means, if two things are proportional, they differ from each other from a constant multiple. So if the derivative and the function are proportional, that means the derivative will equal the function times some constant k. It could be the reverse 2 where k is over here. Either way, it will be just some number. Okay, so that's what proportional means. So we're going to be seeing that set up a lot for this section. So let's take a look at the law of natural growth and decay. So this is essentially what we just mentioned. If y of t is the value of a quantity y at a time t, and if the rate of change of y, which is dy dt, is proportional to the size y of t, then we have dy dt equals k times y. So just remember that that is the same as, we can write it as y prime equals k times y also. So same thing that we just mentioned, the derivative is going to equal the function, the original function, times some constant. And this equation pops up all the time in mathematical modeling. It's called the law of natural growth if k is positive, and the law of natural decay if k is negative. This is also called a differential equation, which if you keep on taking math courses, there is a class that you would take after Calculus 3 called differential equations that essentially goes deeper into this topic. But this is called a differential equation because it involves an unknown function and its derivative. So differential equations, we have a function and its derivative inside one equation, and we see how they're related to each other. Okay, so what we're going to be doing is, what happens if we want to know what the function y of t is? That would be the solution. We're trying to figure out, okay, what's the solution to this differential equation? What sort of solution can we find for y such that the derivative of it equals a number times the equation itself, times the function itself? And what it turns out to be, which we'll mention a little better on the next page, is any exponential function of this form, y of t equals c times e to the kt, where c is a constant, satisfies that differential equation. So let's just see why that is. If we have our function y equals c e to the kt, so c and e or c and k are both constants here, then we can take the derivative of this. We know how to take the derivative, dy dt. That's going to be chain rule. That's going to be c e to the kt, c e to the kt times the derivative of the exponent, which is k. So that is what the derivative would be. And maybe let's just rewrite this for a reason we'll see in a second. Let's rewrite that as k times c e to the kt. So we want to see why this works for our differential equation, dy over dt equals k times y. We just found that this is dy dt, so we plug dy dt in here, k times c e to the kt, and now we plug in k times y. Well, y is right here, so y is c e to the kt. So clearly these are both exactly the same. They're both the same sides of the equation, so we are good. So yes, this does work. So any function that satisfies dy dt equals k times the function y must be of the form y equals c e to the kt. So when we're trying to figure out the solution to a differential equation, the solution is typically a function, and if the differential equation is in this form, then our solution will be in this form, where c and k are constants. Okay, and let's take a closer look at this constant c that we have. So if we plug in 0, if we have the function y of t equals c times e to the kt, and we evaluate y of 0, we plug in a 0 into t, that actually ends up simplifying to y of 0 equals c. So what we could do is we could replace c in the equation and rewrite it like this right here. Y of t equals y of 0 times e to the kt. So here is kind of just a summary of everything we just said, just so it's in one little spot. We have the differential equation. Once again, differential equation, it's an equation that is relating a function to its derivative. In this case, we'll be looking at them in this form. And then the solution to this differential equation, this y value, that y function, in order for this to be true, has to be in this form right here. Y of t equals y of 0 times e to the kt. And then here we have everything labeled. dy dt can also be written as y prime. It's the rate of change of y, or it's the derivative of the function. K, the constant k, is the relative growth or decay rate. Y, or y of t, is the solution function. Y of 0, which we can also write it as y sub 0, which we can pronounce as y naught, is the initial value, and t is time. Okay, so just make sure you know this little boxed in area right here. And let's go one step further. So everything that we mentioned, every example that we mentioned in this topic, in this section, is going to come back to this little setup right here. Okay, so we're going to do this for population growth. So even though we just mentioned what k was, here we can kind of see how it gets its name. If we have dy dt equals k times y, our differential equation, if we have p of t as population at time t, we can rewrite that using a p instead of a y, and it ends up being dp dt equals k times p. Same exact thing that we just did, just using a different variable essentially. And k is called the relative growth rate. And just like we mentioned before, the solutions for this differential equation are going to be the solutions that have the function p of t equals p naught e to the kt. And I put a little note here that p naught is p of 0. It is the initial value. It is a constant. Okay, so that's really nothing new. We're just using different variables to represent population. P for population. So let's see an example here, a couple questions. Example, use the fact that the world population was 2,560 million in 1950 and 3,040 million in 1960 to model the population of the world in the second half of the 20th century. Assume that the growth rate is proportional to the population size. We want to know what's the relative growth rate, and we want to use the model to estimate the world population in 1993 and to predict the population in the year 2020. So we have a few things here. Before we take a look at the information, let's take a look at the questions. We want to know what is the relative growth rate, and we're going to estimate the population 1993 and predict the population in the year 2020. So we have, looks like 3 different questions here. Okay, so something that's very important that tells us how we're setting this up is this question right here. Assume that the growth rate is proportional to the population size. That tells us that we're going to be using p prime equals k times p, or dp dt equals k times p. Which it's kind of obvious that that's what we have to use. That's the differential equation because that's what we just talked about, but that's how you know that we are using that. And I'm going to write that down right here. As soon as we see that it is a differential equation in this form, we know that it has solutions in the form P of t equals P naught e to the kt. Okay, so that's pretty much every single type of question like this with this setup is going to look just like that, maybe with different variable other than P, but it's essentially the same thing. Okay, let's try to figure out now what our variables are going to be. So we're going to have T be in years because that's what we're dealing with. We're dealing with the year. And since we're beginning in 1950 with our data, we're going to have that be time is 0. That's our starting point. Our starting point, time will be 0. So when time is 0, the population is 2,560 million. So what that represents is P of 0 is 2,560 million. So instead of having to write this in million every single time or even write it out, what we can do is we can say that P of t is measured in millions. Okay, that kind of saves us from having to write out a lot of zeros or the word million every time. So there's a little bit of information. Let's take a look at the next piece right here. The population is 3,040 million in 1960. So in 1960, if t is 0 in 1950, that means t has to be 10 in 1960, right? Because it's 1960 is 10 years after 1950. You just subtract the two, and that means that P of 10 equals 3,040 million. Okay, so that means that now we can rewrite this equation right here to P of t equals, we have P naught right here, so that's going to be 2,560 e to the kt. So that's what we have so far. The first question now that we have is, what is the relative growth rate? So the relative growth rate is k, right? So we need to find k. All right, so we are going to find k using this equation, and here's k. We have two things that we need to plug in for. We need to plug in t and then P of t. Then we can find k. So what we have to use is this other piece of information right here. P of 10 equals 3,040. Let's go ahead and plug that in. So we get 3,040 equals 2,560 e to the 10k, right? We plugged in t equals 10, p equals 3,040. Now we have one equation, one variable. Let's go ahead and solve this for k. So we start by dividing both sides by 2,560. And now we can think of it two ways. You can think of it as putting this into logarithmic form, or you can take the ln of both sides. They yield the same result. So we get the ln of the left side equals the ln of the right side. But if you take the ln of e to the 10k, we know that the e is going to cancel, and we're just going to be left with 10 times k. And then all we have to do to find k is divide both sides by 10. And I'm just changing sides so the k is first. So it's that ln number divided by 10. And just for the sake of, we can use a calculator for this, maybe get rounded a little bit here. We get about k is 0.017185. So this is our growth rate. And if we want to write it as percent, we would say that the relative growth rate is roughly 1.7% per year, because you just move the decimal over 2 to the right, and I rounded to 1.7. Okay, so that is our relative growth rate. From this, we now have our updated function. So now our function, p of t, is 2,560 e raised up to the 0.017185 t. So it's important to make sure you're not using the percentage in your function. You're using the decimal form. So now we have p of t. So this function is going to be an estimate. It's a mathematical model for the population t years after 1950. So let's go ahead and answer the remaining questions now. And the next question was, use that model to estimate the population in 1993 and 2020. So I'm just going to rewrite the function here before I do anything. P of t equals 2,560 e to the 0.017185 t. So a common mistake here is you're not plugging in 1993 into t. You have to figure out how many years after 1950 this year is. So we would have to do some subtraction. 1993 minus 1950 equals 43. So 1993 is 43 years after 1950, because remember that was our starting date that we were using. So that's going to be what we plug in. So we're going to do p of 43 equals 2,560 e to the 0.017185 times 43. And obviously we're going to need to plug it in a calculator for this. And we get 5,360 million. So now let's do the same thing for the year 2020. So estimated for 2020, we have our function. And we do the same thing. We say how many years after 1950 is the year 2020. We have to subtract, and we get 70. So that is the t value that we're using. We're evaluating p of 70. And we plug it in, and then once again we're going to have to use a calculator to evaluate this, and we end up getting about 8,524 million. And we could obviously, so 8,000 million is 8 billion. We just used p of t in the millions just so our numbers were a little bit nicer here, so we didn't have decimals. Okay, so it is important to remember that this is just a mathematical model. These are just estimates. And if you wanted to go ahead and look up the actual population in 1993 and the actual population in 2020 and compare them with these numbers, you'll see that the 1993 one is pretty close and the 2021 is not as close. So this is where we would kind of use statistical methods to help us verify accuracy. Okay, so that brings us to the next topic using the same techniques. So that's the one good part. The next thing is radioactive decay. So for those of you who have taken chemistry or physics, you probably know a little bit about radioactive decay. The idea is that radioactive substances decay by spontaneously emitting radiation. So taking a look in terms of the differential equation for this, we're now going to be using an m instead of a p or instead of a y. If m of t is the mass remaining from an initial mass, m of 0, m naught, of the substance after time t, then using our differential equation, we have dm dt equals k times m, right? So same exact thing that we've seen for our differential equation for this section. And the only difference here is that k is going to be a negative constant this time because this is radioactive decay. It's getting smaller. But just like before, we're going to have our function, m of t, our solution function, m of t equals m naught e to the kt. So hopefully you can see how this just keeps repeating itself. We're just using different variables. And I'm sure as some of us have heard, physicists and chemists express the rate of decay in terms of a half-life. And a half-life is going to represent the time required for the substance to decay to half of its original amount. So let's go ahead and see an example. So for example, the half-life of radium-226 is 1,590 years. Something we should keep in mind when doing these problems with the radioactive decay, this number right here represents the atomic weight of the element radium. Radium-226, that is. So that number, we're not actually using it at all in these calculations that we're doing. We have to write it. We can't just write radium. We have to write radium-226 because it's a different isotope. Okay, so just know that when you do these questions for this class, for this chapter, this number is not something that's in our calculations. Okay, so let's see the first part A right here. A sample of radium-226 has a mass of 100 milligrams. Find a formula for the mass of the sample that remains after T years. So we're going to let m of t be the mass that remains after t years in milligrams, and we're going to be we're finding a formula for m of t, and that's actually going to be right here, because we were just told that in the notes right above. So I'm going to go ahead and write that down. So m of t equals m naught e to the kt. So the trick for all of these, something that we're typically going to have to do first, is solve for k. Solve for our decay rate here. So we know that a sample has an initial mass of 100 milligrams. So we're going to have that m of t equals 100 e to the kt. And now we have to say, okay, how do we find k? Well, we're going to find k using the definition of a half-life. So we know, because we were told, that the half-life of radium-226 is 1,590 years. So that means after 1,590 years, the sample is going to decay to half of its initial mass. So that means after 1,590 years, it's going to decay to 50 milligrams, right? We just cut the 100 right in half. It goes from 100 to 50. So what that means is now we can go back and take a look at this function, and we can say that if we plug in the half-life time of 1590, then the new mass will be 50, so it's going to be 50 equals 100, e to the half-life times k. Okay, so that's because, from what we just said right here, m of, get some room here, m of 1590 equals 50. After that many years, the new mass is 50. So now we can solve for k. So we can solve for k by dividing both sides by 100. 50 divided by 100 is 1 over 2, it's 1/2. We have to take the ln of both sides, so we get the ln of 1/2 equals 1590 times k. Divide both sides by 1590. We get the decay rate is ln of 1/2 divided by 1590. So hopefully you're saying to yourself, well, you said that k would be negative because it's a decay rate, and it is negative. That's because ln of 1/2 is actually a negative number. So if you type this all into the calculator, it will give you something negative. So we have, this question was asking for the formula, so we do have the formula now. It's m of t equals 100 e. I'm just going to use this for the k value. I'm just going to rewrite it as ln of 1/2 times t all over that 1590. You could type it in the calculator again like the other one that we did and round it. I'm just showing that we can actually do this without the calculator for now anyway. Okay, so what we just found is we found the formula for the mass of the sample that remains after t years. Okay, so let's go ahead and do another question, a couple questions based on this. We want to find the mass after 1,000 years to the nearest milligram. So first, let's write down the formula. So we're trying to find the mass when time is 1,000. So all we have to do is plug in 1,000 into T and evaluate it. So it's going to be 100 e to the ln of 1/2 times 1,000 all over 1590. And now we should type this in the calculator, and we get about 65 milligrams. So if I were you guys, I would practice just typing this into the calculator just to make sure that you can type it in correctly, because it can get a little bit confusing typing this in using order of operations correctly and making sure you're using parentheses. And also, it's good to make sure your answer makes sense. We started with 100 milligrams. This is decaying. It decayed to 65, so it seems like it makes sense. Next one, when will the mass be reduced to 30 milligrams? Let's go ahead and write the formula down again. Okay, so we have our formula. Now we're looking for the mass. So we're looking for, now we're given the mass, and we're looking for the time. When we are looking for the time, we're given the mass. So what we're going to do is we're plugging in 30 into m, and then we have to solve this for t. So solving this for t, we have to divide both sides by 100. 30 divided by 100, I'm going to simplify that to 3 over 10, just to make the numbers a little smaller. E to the ln of 1/2 times t over 1590. And then we just solve this the same way how we solve for k. We take the ln of both sides, ln of 3 over 10 equals the ln of 1/2 times t to the, or over 1590. And now we can multiply both sides by 1590, and at the same time, let's divide by ln of 1/2, and we get we get 1590 times the ln of 3 over 10 divided by the ln of 1/2. Okay, and then we type that all in the calculator, and we get 2,762 years. So that means it started with 100 milligrams, and then after 2,762 years, it decayed to 30 milligrams. Okay, and then the last application that we're going to be using this idea for is Newton's law of cooling. So Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. Okay, so we're going to have some variables here. If we let t of t, so a little bit confusing because we have t's everywhere, capital T of little t is going to be the temperature, so capital T is temperature, lowercase t is time. T of t is temperature of an object at time t, and T sub s is going to be the temperature of the surroundings. So a little bit easier to see because we have the S, temperature of surroundings, S for surroundings. Then the formula for Newton's law of cooling as a differential equation is going to be written just like this. dt, the derivative of temperature with respect to time, is going to equal K times T minus Ts. So that's the temperature of the object minus the temperature of surroundings. It's the difference in the temperature between the object and surroundings. So this is a little bit different than what we used before, right? Because what we used before, we had K times like Y, K times M, K times P. So in order to be able to use the same solution function from last time, we have to do a little bit of variable change here, and we're going to let y of t equal t minus t sub s. If we do that, then that's going to replace this with a y, and then it becomes this right here. dy dt equals k times y, which is what we are used to solving, and we know how to solve that. And the reason why, hopefully it's pretty obvious why this becomes y, because that's what we wanted it to become. The reason why the derivative of the temperature can equal the derivative of y is because the temperature of the surroundings is a constant. We know the derivative of a constant is 0, so that means y prime equals capital T prime. Okay, so that's some using variable change here and rewriting it, and we know that this differential equation has these solutions for it. So the issue is, once we solve this, we're going to have it in terms of a y, but then we can go back and solve for t using the fact that we let y equal t minus t sub s. Okay, so hopefully not too confusing. We pretty much have three things. We have, three things. We have our differential equation and the solution, which we're used to seeing, but then we also have this last portion right here. Okay, so let's see an example. Let's see how this works. We have a bottle of pop at room temperature, which is 72 degrees Fahrenheit. We place it in a refrigerator where the temperature is 44 degrees Fahrenheit, and after half an hour, the pop has cooled to 61 degrees Fahrenheit. We want to know what's the temperature of the soda pop after another half hour. We're going to let capital T of T be the temperature of the pop after T minutes. So based on Newton's law of cooling, we have this right here. So let me go ahead and write this down here. We have dt, the rate of change of the temperature, equals K times T minus 44. Right, so this temperature was the temperature of the surroundings. That is the temperature of the refrigerator, which is a constant 44. And now what we're going to do is what we mentioned. We're going to use this little fact right here. We're going to let y equal t minus t sub s. So y is going to be this chunk right here. And once again, the reason is because then we can write it as dy dt equals k times y, which is how we're used to seeing, and we know how to solve that with our solution function. And what we can actually do from this is we can figure out, because if you remember, let's think ahead a little bit. If we have this differential equation, we know that the solution function is going to be y equals y naught e to the kt. We're going to need y naught, right? We're going to need that initial value. We can find that, same as y of 0, y naught, y of 0, same thing. We can find that by plugging in and evaluating the temperature, the initial temperature of the object. We know the initial temperature of the object because we're told that it's 72 degrees. So that's going to be y of 0 equals 72 minus 44. So we get y of 0 equals 28. So now from all of this over here, now we have dy dt equals ky, and we also know that y of 0 equals 28. Okay, so from this we are going to know our solution function, right? We know our solution function like we just mentioned. Y of t equals y naught e to the kt, and we just said that we can replace y naught with that 28. Okay, so just so it doesn't look too cluttered, I'm just going to erase it and plug that right in. Okay, so from all of the stuff that we just did, we basically got these two equations, the differential equation and the solution, and now it's very similar to what we've already done. So I'm going to go ahead and write these on the next page just so we can kind of start a little fresh here. Well, we'll just write this one because that's one that we're going to be dealing with. We also have this piece of information right here. After half an hour, the soda pop cooled to 61 degrees Fahrenheit. We're going to use this piece of information to help us find K, just like we did in the past. So we can do that because that means that T of 30 equals 61. The issue here is, maybe the one tricky thing is, we no longer have the function with a capital T. It's not in terms of the temperature, it's in terms of Y. So what we're going to actually have to do here is go back up to this portion right here, Y equals T minus 44, and use that. So that's Y of 30 equals 30, or rather, Y of 30, let me write down the function just so we don't mess that up. It was Y equals T minus 44. So that means Y of 30 equals 61 minus 44, because that's our capital T here. So this is going to give us, what does that give us? 17. Okay, so Y of 30 equals 17. So that's what we have to use. 30 is our T. Our Y of T is 17. Plug those in and let's solve for K. So we get 17 equals 28 e to the 30t. Divide both sides by 28. And we take the ln of both sides. ln of 17 over 28 equals 30t. Divide both sides by, oops, sorry, that should be K. 30K, 30K, 30K. Divide both sides by 30. That gives us ln of 17 over 28 over 30. And plugging that into the calculator, we get, it's approximately negative 0.01663. Okay, so from all of that, we get the function Y of t equals 28 e to the negative 0.01663t. Let's go one step further before we even answer this question. Let's use this right here, and we know y. We can use this and then solve for t to get the function as t equals. So using y of t equals t minus 44, we end up getting capital T, if we solve this for t, equals 44 plus y of t. Let's go ahead and plug in the function y of t, which is right up here above, 28 e to the negative 0.01663t. And now we can finally answer our question. Okay, so before we answer our question, let's just go ahead and review what we did. We started off with the differential equation written like this, but we wanted it in this form. So we had to let y equal this portion right here, so it would be in the correct form. So we get it in that form, and then we need to find the solutions. So the solutions are in this form. We had to find y sub 0. We had to find the initial y value using this right here. So once we found that, we had to go back over here, go back to this equation, and then we had to set this up to solve for k. And then once we solved k, we get y, and then we can find the temperature equation of the soda pop. So it's always a little bit more confusing when you have to use this change of variable. You had to let y equals t minus t sub s. So hopefully it wasn't too bad, but now we have this equation here, which represents the temperature of the soda pop t minutes after it was put in the fridge. So all we have to do now is plug in for little t, and we're looking for t of 60 because it says what's the temperature after another half hour. That's 60 minutes total because it was a half hour first, half hour again, 60 minutes total. and we go ahead, plug it in this equation. That's 44 plus 28 e to the negative 0.01663 times 60, and that ends up giving us about 54.3 degrees Fahrenheit. Okay, so that's probably the hardest type of question that we'll see from this section, but you can kind of see how it's kind of interesting because we were able to figure out this type of question, which we do in everyday life working with a refrigerator. Okay, one more question. How long does it take for the soda pop to cool to 50 degrees Fahrenheit? So we have our function, and 50 is the temperature now. So we're trying to find time. We're trying to find time when capital T is 50. So that's going to be 50 equals 44 plus 28 e to the negative 0.01663 t. Now we solve this for t. So subtract 44 on both sides. We get 6 equals 28 e to the negative 0.01663 t. Divide both sides by 28, and after we do that, we have to take the ln of both sides, so it's going to be the ln of both sides. Then we have to divide both sides by that negative number. And plugging that in the calculator, we get about 92.6 minutes. So after 92.6 minutes, or about an hour and 32.5 minutes, it will cool to 50 degrees Fahrenheit. Okay, so that is it for this chapter.